Good morning, everybody, or I guess good afternoon, depending on where you may be. Thank you for joining us today for today's webinar in a series called Acrylamide Grout Saves the Day for TBM in Portland, Oregon. My name is Jessica Williams, and I'm the marketing manager at Avanti, and I'll be playing the moderator host today, making sure that we get the most out of the next maybe 75 minutes. We may not go the full 75, but we think we'll go over the 60, so we wanted to have that time honored. Before we jump into introducing our speakers for the day, a couple of just housekeeping items. We're going to host a Q&A session at the end of this presentation. So at any point, during any time, you think of a question, don't wait. Go ahead and input it in the right-hand side. You'll see the question drop-down box, enter it, and we'll try and get to as many questions at the end of this broadcast as we can. I'm going to let each of our presenters briefly introduce themselves and give you a 30-second view into who they are, what they've done, and why they're here. So why don't we go left to right? Ken, I'll let you start it off for us.
Well, my name is Ken Fott, and I've been in the grouting business since 1966. I've been working all over the world and completed now close to 800 projects in drilling and grouting. Some of them were very small, some of them were quite large. One was the largest dam on Earth. I worked on the Panama Canal expansion recently, and the project we're going to talk about today is really quite a large project.
Awesome. Thanks for being here, Ken.
I'm Jacob Swanson. I'm the director of our geotechnical division here at Avanti. I have about 20 years in the grouting industry. Started in the field running projects, doing everything from soil stabilization to leak stopping in various different applications. Just looking forward to today and hearing more about the project that Ken will be presenting.
Thanks, Jake. Britt?
And last but not least, my name is Britt Babcock. I'm the president with Avanti International, and I started my career over 30 years ago now in the construction and engineering industry, and started as a geotechnical engineer for almost more than a decade, and then shifted over into technical products and civil engineering products, and have been in the grouting industry for I think we're going on my 14th year now, but got my license as a geotechnical engineer and really enjoy how everything that we do touches the earth. And so it's fun to be a part of, see how the injection grouts correspond and interact with the geology. And Ken's going to go into that in more detail today about how that affected the project he was on and the positive things that came about it. So thank you.
Awesome. Thank you all. Looking forward to the next hour or so. Before we get into the presentation, we'd like to launch a poll question. And this is just, we like to see where you are located. So on your screen, you'll see we're at what area of the U.S. or international are you located. We'll give you about 30 seconds to answer. We just like to kind of know where we're at. So responses are coming in. Give it about 5 or 10 more seconds, collecting responses. All right, I'm going to close the poll. So I don't know if it's up on the screen. I can see it on my side. So we've got about 24% of our attendees in the Northeast, 18% in the South/Southeast, 22% in the Midwest, 24% in the West, and 11% international. So really almost equally spread for the most part throughout the U.S. So thank you all for that.
Great distribution of people around the globe, around the country and around the globe.
Yeah,
that's been fantastic.
Great to hear. We'll have another interactive poll question throughout too, so thank you all for doing that. And now we're going to jump right into the presentation, and I believe, Britt, you're going to take this off for us, so I will give you control, and you're on.
All right. Well, what we want to do is we want to start by just defining what injection grouts are, and I'm going to go through, and Jake and I are going to explain to you kind of the family of grouts that exist out in the world. And then Ken will obviously take the one grout that he used on his project and dive into the details around that. But we think it's best to kind of explain what they are so everybody has a clear base fundamental understanding. So what is an injection grout? An injection grout is actually a liquid resin like what you see on the left-hand side here. There are two liquids being poured together that cure into an impermeable solid in a predictable time frame. This happens to be AV100 that's gelled. In this particular sample on the right, it's the gel on the top, neat gel if you will, but then it's been impregnated into sand below. So that's the definition of an injection grout. That's true if it's a urethane grout. That's a resin that then either interacts with a part B component if it's a one-to-one, or if it interacts with water and creates that curing process that cures into a impermeable solid form that's impenetrable. What are the goals for injection grouting? When we talk about injection grouting or grouting for water control or stabilizing soils, a lot of the jobs get in a lot of different aspects, whether you're controlling groundwater in a break-in, break-out on a shaft for a TBM, or if you're controlling groundwater on a shaft advancement for a mine, or groundwater in a manhole or a wet well or a basement underground parking garage. There's a lot of different projects that grouting gets used on, but when you boil down to what the ultimate goal is of the grouting technique or application, it comes down to either you're stabilizing the soil and rock or you're controlling the groundwater. So it's really fun it helps you understand kind of what the injection grouting process does and what it accomplishes. What are the injection grout families? Well, the primary grout families consist of cementitious grouts. That's your ordinary Portland type 3 or type 1-2 also could be considered a cementitious grout. Ultrafine grout is another family within that, and we're going to a little bit more detail on each one of those. Then you get into solution grouts, which what I'm calling are solution grouts are sort of what people call chemical grouts, but solution grouts are the industry term of which we're going in that direction. These are the polyurethane grouts are one part of the subset of the solution grout family. That within the polyurethane family, you have a hydrophilic and hydrophobic. And what differentiates real quick between cementitious grouts and solution grouts is particulate versus non-particulate, if you will. Cementitious grouts have particles. Type 1-2 could have anywhere from 75 to 100 micron size particles. Type 3, 15 to 25 microns. These range a little bit. And ultrafine grouts, anywhere from 3 micron average up to 8 micron average, depending on if you're looking at an ultrafine or a microfine, and as low as 1.5 if you're looking at a superfine. So again, particulate grouts for cementitious, solution grouts non-particulate. So to continue on within the family of solution grouts, the other subset, as that tree branches down in the family, if you will, the chemical reactive grouts, so the acrylamides, the acrylates, the acrylics, and the sodium silicates. So talking about the cement and cementitious grouts, again, ordinary Portland cement type 1-2 does get used. In this slide, we're showing type 3, average micron size. We're saying 15 to 20 microns here. To give you a size we've referenced, we've got it here to the right. And then under the cementitious grouts, we've got the microfine average of about 8 microns, ultrafine of 3 microns, superfine at 1.5 microns. To put that in perspective, what does that look like, right? The diameter of a human hair on average is about 70 microns. So if you feel your hair, okay, that's 70 microns. That feels pretty small, right? One hair. So if you think about 8 microns, that's the equivalent to this red blood cell or an average micron of microfine cement. Then 2 microns, if you just to size that up by 1, will give you the average particle size of ultrafine cement. So just to put that in perspective, 3 microns is basically the same particle size as smoke. So if we were to have a cup of ultrafine cement and powder here, that's how it comes in, and I put my finger on it and I tapped it, it would go airborne. So, because it's so fine, which what's that fineness or that small particle size, average particle size helps its ability to permeate into soils, as well as into fine cracks and fissures and things like that. What makes up the composition of a cementitious grout? Well, it really comes down to two primary components when it comes to composition. There's ordinary Portland cement and some type of pozzolan. The pozzolans can be a slag-based, can be pumice-based. I'm showing in this picture a pumice mine here, Hess pumice mine in Idaho, southeast Idaho. These two components get combined together and get ground down to the particle size which we're trying to achieve. So why does the particle size matter? And also, one of the other components get used within that gets added to the mix when you're mixing an ultrafine cement and a type 1-2 ordinary Portland cement or a type 3 is a superplasticizer, or another term in the industry is water reducer. What that does is actually change the charge on the particles within the mix and forces them to repel each other, and it makes it very liquid, very fluid. So you can take something that's relatively sticky with a low water cement ratio, add a very small amount of this chemical, a superplasticizer, and it'll make it look like a pancake. It's pretty fascinating to watch. I think we have a video of that on our website. But particle size and superplasticizers help allow the ultrafine cements to become very fluid-like. In this particular example, we've got two columns here that are filled with AS-Team 30 mesh sand, and we've pumped at a low pressure, less than 10 psi, and low volume, an ordinary Portland cement grout up into the sand to try to permeate that sand. You can see here, we only got about 2 feet, or about 20 inches up the column before it stopped permeating. Whereas here on the ultrafine cement, this particular ultrafine SD from US Grout, was pumped up and actually traveled the entire length of the column. So just a difference in how things perform in that regard. An example of how they can penetrate into small fractures and fissures. The black happens to be ultrafine cement. Just happened to be how the picture turned out here, to be black in the fractures and fissures. So jumping into polyurethane grouts now, if we're going to jump into the solution grout family. Again, polyurethane grouts are made up of hydrophilics and hydrophobics. Hydrophobics have a strong affinity for water. Think of hydro, that's water. Philics likes to be filled with water. Hydrophilics were the first grouts to be invented, single component. When they interact with water or mix with water, they react and cure. Hydrophobics, on the other side, they still react with water for the most part. There are some that are A and B that will react together. But think of fear, right? A phobia, fear. They have little to no affinity for water. They use a little bit of water to react for the most part, but then they become not affected by wet, dry seasons, things of that nature. And so hydrophobics oftentimes are mixed with a catalyst, or in the industry an accelerator, and then injected, and that little bit of that water in the soils or the moisture in the soils will react to grout. Again, there are hydrophobics that have that are 1-to-1, part A, part B as well, that react on that chemical reaction. Polyurethane grout viscosities can range from as low as 35 to 50 centipoise to as high as 3,000. Water being 1 centipoise, to put that in perspective, so the lower the number, the much more fluid the material is. 3,000 centipoise is like honey, to put that in perspective. The reaction times can be as fast as 3 to 4 seconds. That's a chemical reaction type material where you have a part A and part B, to a high range of 30 to 45 seconds, whether it's a single component or a hydrophobic with an accelerator. They are sensitive to temperature, so the colder it gets, the longer it takes to react. The warmer it gets, the faster it reacts. So hydrophilic polyurethanes, again, the first to be invented, toluene diisocyanate, or you'll hear the term TDI. They can make a gel, a foam, or a solid. They're single component, as I mentioned before, typically moderate expansion, 4 to 6 times, or 400 to 600%. They're generally flexible. They're hard to accelerate because they're single component. They react with the water. A lot of the products out there in the market space have potable water, or potable, if I'm going to say that correctly, potable water approvals by WQA, or they meet NSF 61 potable water approvals, and they have a fair resistance to chemical. Here's an example of a part of a single component with water, then mixed, actually expands and creates that flexible foam type material. Hydrophobic polyurethanes are methane diisocyanates, or MDI. They can create a foam or a solid. They tend to have much higher expansions. They can be as low as 4 times to as 30 times, or 400% up to 3,000%. They're dual component. They can be a resin with a catalyst, typically a hydrophobic resin with an accelerator. We call it a catalyst because that's the technical term, but it is called an accelerator in the industry. And water's the reactant to help drive that. And there is a resin to resin chemical reaction sometimes on some of the hydrophobics as well. They can be flexible to semi-rigid to rigid. They can be accelerated by adding more accelerator or catalyst. They also have potable water approvals that meet NSF 61 and good chemical resistance. Here's a chemical reaction, one of part A and part B. That's a 1-to-1 mix with a 30 times expansion. It blew its way, it just topped out like lava out of the cup. So there, I'm going to stop and I'm going to hand this off to Jake. Jake, you are up and ready to go.
Thank you, Britt. So continuing on with the solution grouts, we're going to look at the chemical reactive grout family now, which consists of the acrylamide, acrylic, acrylate, and silicates. All of these systems are going to be 2-component, A and B, and generally they're used at a 1-to-1 ratio. Some of these multi-ratios can be utilized, but most commonly it's a 1-to-1 ratio where they're used. These are also very low viscosity, so water having being 1 centipoise. The acrylamides and the acrylics are going to be 1 to 2 centipoise, so the naked eye you cannot really even tell the difference. And then acrylates and silicates, still very low, but push up towards 3 to 12 centipoise. There's also some high solid acrylates that are actually even a little bit higher than that now, around 20 centipoise. So due to that low viscosity, and partnered with the fact that they do not have any particles, as Britt had mentioned, these allow these products to permeate anywhere that water can travel. So pretty much many different types of soils, cracks and fissures, if the water can travel through there, these products are going to be able to penetrate and travel in as well. They have controllable set times, the acrylamides, acrylic, and acrylates. They can be adjusted anywhere from just a few seconds all the way up to many hours. We say 10 hours here. Once you get past that, you start to lose a little bit of control on the gelation range. So it may be a wider range where it sets, but so very, very wide range. So depending on the application, if you're stopping water, faster set time may be beneficial, or you may want that water, if it's seeping or moving through the soil, you may want to use that to your advantage with a longer set time so that that water is transporting the material to where you want to get it. Silicates, generally, the set times are going to be under 1 hour. Slides are not advancing for me.
There we go.
There you go. All right, so the chemical reactive grouts, just a few pictures to show how these work. 1-to-1 ratio, same viscosity as water. Here we've dyed the part A and the part B, 1 blue, 1 yellow, so when they combine, they turn to green. This is important in the field to make sure that the pumps, which are going to be a 1-to-1 ratio, make sure that they're actually pumping properly. We're getting both components. And additionally, these products, if the dye was not in them, they're crystal clear. They look just like water. You can't differentiate them. So obviously, if we were stopping water, we don't want to be pumping grout and not being able to differentiate it from the water that's coming, infiltrating into a structure, let's say. This gives us a means to be able to differentiate and adjust our set time if we have too much waste or if we're losing material and having it go where we don't want it to. With these, there's no expansion like with most of the polyurethanes. So what you pump is what you get. If you pump 1 gallon of A, 1 gallon of B, ultimate product, you're only going to yield the 2 gallons that were pumped. Non-toxic when cured, they're great for controlling water. As you can imagine, if you have something that is like water traveling through the soil and then turn to a gel, it's filling all that pore space between your soils and blocking off the pathway where water can travel through there. So very, very good with water control. And then the acrylamides are actually, they have the NSF 61 potable water certification as well now. Move on to the next slide. So when we look at the acrylamides, or our AV100 is our particular one, it's a mix of acrylamide, methylene bisacrylamide, or MBA. These are organic based. They've been used since the 1950s. In the grout applications, these are actually originally developed for seepage management around dams and reservoirs. So you can imagine you put in a new concrete dam, concrete is holding back the water, but what about the surrounding soils? So that's where they were originally developed. Since then, they've expanded into many different market spaces. They have a long design life. The Department of Energy did extensive testing on our AV100 at a 20% grout concentration for hazardous waste contamination and encapsulation in Oak Ridge, Tennessee. And through that testing, they developed that in the soils, the AV100 had a 362-year half-life. So once it's there, it's going to be there for a long time. We mentioned adjustable set times, so wide range, very beneficial depending on the soils and the application that we're getting into. Manageable toxic component, so all of our customers that we work with and anybody that's ever going to work with these goes through training on proper PPE, proper management, working with the products. And then inert, non-toxic, and irreversible when it's cured. So once the acrylamide turns to a solid, the chemical has actually changed. It's turned to a polyacrylamide. It's important to know that once it cures, it has changed, because polyacrylamide is very much different than acrylamide. And that's the cured product has that NSF 61 certification for potable water use. Acrylates, these are also organics. They've been around since the 1980s, and they're a variation of acrylamide, just a little bit more refined. These are also used for controlling water. They're great because they're another solution grout and turn to a gel. Very similar products. Short to medium design life. I believe that same testing that the Department of Energy did established somewhere between 75 to 100 year half-life on these products. And then they also have a very wide range of adjustable set times and a non-toxic component. Still the same PPE requirements between acrylates and the acrylamides. Yeah, then we'll move forward. And then sodium silicates, or water glass. These have been extensively used. They've been around since the 1800s. They are inorganic. In the industry, there's a little bit of contention. It's widely considered to be temporary, and the expectancy behind them is really dependent on the geology and what is there. So many people say 10 years, some people say 20 years. There's some differences between the reactants that you use with it. I can adjust that as well, but generally they're considered temporary. Used for excavation support and underpinning, good compressive strengths. They're generally not used for water control. For water control applications, you have to use a very high concentration of the sodium silicate. And as you're pumping into groundwater conditions, you can wind up with many irregular, you have mixing of the groundwater and the product. So you can wind up with a little bit of irregularity there. And then these are susceptible to syneresis depending on the reactants that are used. And generally they're going to have that shorter set time. So a little less variability there. Moving forward, I'm going to go into where injection grouts are used. So hopefully now we have a pretty good basis of the different products and kind of how they're used, where they can be used, but we're going to dive into it a little bit more here. So mainline sewers, laterals, and manholes. This is something that a lot of people don't even realize. I think below grade assets in general, the general public and many people don't realize that this is a major issue. If we have infiltration going into our collection systems, ultimately that groundwater, clean groundwater that's entering the sewer now is sewage. So it has to be treated. And it's a large problem. Generally, these are going to be the acrylamides and the acrylates that are used for sealing these components, because most of it's not man entry. So sealing those joints, you require a 2-component product. You need an adjustable set time, and you need something that's going to be able to stop that water relatively quickly. Moving forward, soil stabilization and excavation support. You can see here the granular soils have been stabilized underneath this footing or underneath the foundation here so that they could create a vertical cut and not have that soil slough out from beneath the neighboring structure. Ultrafine cements are commonly used. Polyurethanes can be used depending on the soils. And it really depends on the design criteria, whether or not any of the acrylamides, acrylates, or sodium silicate would be, depending on the strength requirements and what the soils dictate. As I mentioned before, Oak Ridge, Tennessee, where the Department of Energy did extensive testing, hazardous waste containment. So because we can fill that pore space with these products and prevent groundwater from moving, we can also hold groundwater in place and create curtains and blockages to prevent any waste from traveling to neighboring areas. Subways and tunnels, extensively used here, new construction and existing, so rehabilitation. On the right, you can see this is a subway tunnel where they had leaks coming in from various different areas that they needed to seal. This was in a northern environment where it would develop ice, and they didn't want the ice falling in and damaging any of the train or any of the equipment. So move forward on that one. Mines, tunnels, slopes, and shafts. So I'm sure that you're seeing kind of a general theme here. Anything below grade that is susceptible to groundwater where you don't want it, these products are used. So mines, tunnels, slopes, shafts, adits, all of those are included. Concrete and earthen dams, we touched on those before, everything from the drainage gallery to the surrounding soils and everything in between. Beneath structures, so oftentimes, for any of the geotechs that are on here, oftentimes people want to build structures and they don't want to invest enough money into understanding what is beneath that structure. When that happens, oftentimes they need to do some soil remediation. This is the Rose Bowl. They used ultrafine cement on this project to help modify the soils to increase their bearing capacity for the structure. Break and breakout in shafts, working on a few of these right now, a couple different customers. Tunneling in TBMs. I could go in, dive into this animation, but I don't want to take away from the project that we're going to be talking about, so we'll keep moving forward here. Pre-excavation and dewatering. Oftentimes on large shafts or on excavation jobs that are extending into the groundwater table, if it's a large project, it's going to be open for a long time. It may become cost prohibitive for dewatering. In some of those situations, if the geology dictates, injection grouting can be used to create that water barrier around and beneath the structure so that dewatering isn't necessary and just provide some additional control on these types of projects. And then today's focus, the geotechnical grouting and tunnel grouting. This is where I pass it off to Ken. Exciting part of the presentation.
Awesome. Thanks, Jake and Britt. Just before we jump into the rest of Ken's presentation, I'm going to launch one more poll question for you. There we go. It should be launched. We'll give you about 30 seconds. The question is, how many specialty grouting projects have you worked with or on? 0, 1 to 2, 3 to 5, 5 to plus. We just like to get a good grasp on where at in your career you are. If you're new to this, if you're very established, we'll give about 10 more seconds. Votes are coming in. All right, looks like I'm going to close the poll. So I'm not positive that you can see it on the screen, but the answers say 13% have 0, 25% 1 to 2, 13% 3 to 5, and almost 50% 5 plus. So with that, we'll move on to Ken, your part of the presentation, giving you mouse control, and you're on.
Okay. Well, today I had to pick one case history from a long list that I mentioned before, and I picked this one largely because it's close to my hometown. It has interesting geology, and it used many types of grout, and it is relevant to work that's going on today. It was a soft ground tunneling project, and we'll talk about one specific case, one little small part of the project. The work was done in Portland, Oregon, and it's part of the EPA's combined sewer overflow remediation project. The tunnel grade is 60 to 80 feet below street level, and there are 6 construction shafts and 5 tunnel segments. The combined sanitary and storm drain wastewater collected by the tunnel flows by gravity to an outfall that's connected to the Portland West Side CSO tunnel, and from there it goes under the Willamette River to the Swan Island treatment plant. The construction sequence required sinking the shafts in highly permeable soils below the water table. So permeable, the dewatering for the shafts was absolutely impossible. Accordingly, they had to stabilize the soil around the shaft before they could excavate them. It's not, there it is. This project was a happy place for grout suppliers and grouting consultants. Cementatious grouts were used for shaft construction. Cement grout was used to stabilize the coarse grained soil, and ultrafine cement was used to stabilize running sand and conditions on the tunnel. Every species of solution grout except sodium silicate was used. And polyurethane grout was used to seal the cracks in construction joints in the structures all over the project. And chemically reactive grouts were used to seal cracks in both acrylamide and acrylate grouts were used to control groundwater at various locations. I have to go back one. Do we have a way to go? There we are. The tunnel routes shown on this slide, the work started at shaft GLI in the upper left-hand corner, and there was a pipeline section shown in red. Then the tunnel wandered around across the Giles Lake industrial and port part of Portland, the city of Portland. It was part of the West Side CSO contract, but there was an eminent domain dispute over this property that's shown in green that was going to delay the project by maybe as much as 4 years. So this project was removed from the CSO and rebid after the lawyers had their day in court. Once again, it's not changing for me. The Nikolai shaft is shown in this photo. It was the receiving and launch pit for the CSO tunnel, and it crossed under the Willamette River. And this area in the yellow circle was the termination of the original CSO Balch Tunnel alignment. They started construction in a jet grouted zone, and when they got down about 50 feet, they found a gap between some of the jet grout columns. It resulted in a bottom heave. It flooded the shaft in about 10 minutes, filled it with running sand and water. The laborers in the pit barely escaped, but all the contractor's equipment was lost. The contractor went ahead and grouted the bottom plug again with Portland cement grout and started to clean out the shaft. And they got down about the same depth and had another blow-in event. So the owner decided to abandon shaft M on the CSO project and include redesign and reconstruction of the shaft in the Balch project. During the project, we went ahead and used superfine cement to repair the jet grouted bottom plug and stabilize the running sand. And then we also used polyurethane grout to seal the cracks and fissures in the connection between the old Nicolai shaft and the new shaft M. And this one isn't, there we go. Getting back to this slide, there were unforeseen ground conditions at shaft D, which resulted in a sand run-in and some void formation. Microfine cement grout was used there to stabilize the running sand and to fill the voids. And at shaft L, cement bentonite grout was used to stabilize a deposit of open work cobbles before the shaft could even be built. And also on the project, there were 2 tunnel interventions required. The first or the second tunnel intervention was here, and it was to replace the cutter teeth on the tunnel machine. The first intervention was immediately after we broke out of shaft L, the tunnel machine went offline and got stuck. And this is the intervention that we're going to focus on today. Before we go into the design of the tunnel intervention, I want to give you a little bit of a project overview. All the tunnel access shafts were originally designed with jet grout soil modification around the shaft. But in taking into account the problems at shaft M, the contractor, J.W. Fowler, proposed an alternative construction method using the cutter soil mix system for consolidation of the ground at the shafts. The cutter soil mixing system uses a very large mandrel and 2 counter-rotating cutter wheels at the bottom of the mandrel. And the machine pushes it into the soil. The cutter wheels turn, loosen the soil, and mix it with the cement grout that's pumped down through the mandrel. And then after you extract the mandrel, you can vibrate in a steel H-beam to add additional strength. Successive panels are overlapped slightly to form the walls of the shaft, and then you can excavate the material from the shaft interior. This is a photo of the wall of a completed shaft. The CSM performed really well in the silty sandy gravel soils, but there were some problems with drilling through cobble layers and the open work cobbles. In this photo, you can see the cutter marks from where the wheels were turning. And also you can see that in this case, we're 50 feet, 60 feet below water table, and the shaft is completely dry. It's remarkably tight. After the shaft is excavated, the launch block is constructed and the jacking frame is put in place and the tunnel seals are constructed. Then the tunnel machine is lowered into the jacking frame, pushed forward through the tunnel seals and the jack block, and begins tunneling by pushing additional pipe segments behind the machine with the jacks shown in the photos. This is the tunnel machine. It's a Heron Connect closed-faced earth balance machine. And during tunneling, bentonite drilling mud is injected in front of the tunnel machine as it rotates. The pressure of the bentonite mud balances the earth pressure that would be pushing into the machine, also balances the groundwater that is trying to push in. And the spoils are removed during cutting through ports in the face and then pumped away for disposal. There's an airlock in the trailing gear behind the tunnel machine, which can be used to keep water from entering the tunnel and flowing back to your launch pit. Also, it gives you a way to access the interior of the machine in an emergency. The cutters have to be designed for the anticipated ground conditions that you're going to go through, and they're intended to operate for the full length of the push, because it's really very difficult to go in and change the cutters as you're going along. So you need to know and understand the geology that you're going to encounter, even more so than what you would get from just looking at the exploration boring logs that were done for the tunnel. So I'm going to say a little bit about the regional geology. The project is located in a geologic structure known as the Portland Basin. The basin is a faulted and folded syncline located in Oregon and Washington at the confluence of the Columbia River and the Willamette River. The basement rock is Columbia River basalt group, and at the west margin of the basin, the basalt is uplifted along a fault known as the West Hills Fault, which goes right next to the Balch Tunnel. The Columbia River basalt is overlain by alluvium that is deposited in the old Columbia River and Willamette River valleys. And the bottommost unit is known as a Sandy River mudstone. Above that is 100 to 350 feet of well-consolidated sandstone and conglomerate called the Troutdale Formation. And overlying the Troutdale Formation is flood deposits comprised of cobbles, gravels, sands, and silts. The flood deposits are known as the Missoula flood, and they're embedded with alluvial fan deposits originating from the West Hills. Also, there are deposits of Mount St. Helens volcanic ash embedded within the Missoula flood. And on top of the Missoula flood, you can find recent volcanics, boring lavas and silt, so forth from volcanic eruption. If you're not familiar with the term Missoula flood, it refers to catastrophic flooding in the Pacific Northwest during a period of global warming at the end of the last ice age. The North American ice sheet blocked all of the drainage from the Rocky Mountains up in this area and formed a lake that is estimated to have been about 500 cubic miles of water. It's a very big amount of water. To get that in scale, it's enough to cover the entire metropolitan area of New York with 765 feet of water. When the ice began to melt, the west margin of the lake collapsed and released floods that spread across the shaded areas here in northern Idaho and Washington. And all of this water spread out across this area, but it has to funnel through a narrow gap at the Horse Heaven Hills that's outlined here in with the red circle. This is a photo of the Wallula Gap through the Horse Heaven Hills, current day, and I drew a line in there showing the highest elevation that geologists were ever able to map flood scars. It's about 960 feet above the current river level. And if you do open channel hydraulic calculations downstream and using the gradient of the flood scars, you can calculate that there was about 1.66 cubic miles of water discharging through this gap at the peak of the flood. The ice dams reformed and collapsed and reformed many times during the late stages of the Ice Age. The repeated floods scoured most of the soil and rock off of all of northern Washington and deposited in the lower Columbia Valley and in the Willamette Valley, where it makes for really interesting tunneling conditions. The Portland Harbor and Industrial District is shown here in this map. It it is between the Willamette River and the West Hills escarpment from the Portland Basin. There's a deeply incised creek called Balch Creek that formed an alluvial fan deposit in this area. And now that alluvial fan is buried under Missoula flood deposits. And the tunnel project area is right here. So we crossed out of Missoula flood into Balch Creek fan deposits, back into Missoula flood, et cetera, during the excavation. This cross section shows the location of Shaft Mary. The brown material is Missoula flood deposit. The yellow material is characterized as dredged fill, but in fact it's wood debris, buried logs, foundry waste, incinerator ash, car bodies, anything that they could dump while they were filling in Giles Lake in the early 1900s. And then also at Shaft Mary, we ran into an undetected deposit about 10 feet thick of Mount St. Helens ash that had been washed into a low spot sometime after the eruption. And it was a sedimentary deposit, but almost 100% Mount St. Helens ash. To orient this map, the match line here at the top is the left match line from the previous map. The blue-green unit is characterized as open network gravels with cobbles, and the gray unit is characterized as gravel alluvium. When the CSM rig hit the blue-green unit, it stopped cold, pulled it up. There were large cobbles wedged in between the cutter wheels. So he cleaned it out, put it back in, and get the same problem again. And eventually we concluded that whenever we got to the cobbles, they would just roll underneath the cutters until they wedged it up, and they weren't being ground up. So we had to do something to stabilize the cobbles in place well enough that the cutters could get through it. So this area was grouted using cement bentonite grout, and that stabilized the cobbles, held them in place so that they could be cut up. The samples shown in this photo, outlined in blue, are from the original exploration borings. And the borings were done west of the actual shaft location. The blue-green zone is represented as cobbles and gravel. But when we got into the actual shaft location, it was an open work cobble zone. I don't want to belabor this change condition because there was a building on the site before when the explorations were done, and the building was demolished before we started the shaft. The material that we used to stabilize the cobble zone was cement bentonite grout. We batched it at 160 gallons of 2.5% bentonite prehydrated slurry, 840 pounds of Portland cement, and the yield was 200 gallons of thixotropic slurry per batch. The materials could be pumped through a 1-inch pipe at about 200 psi pressure, and when they extruded out in between the open work cobbles, the velocity and pressure dropped and the material reached a gel set condition, held it in place. Then when it cured, the average strength that we got out of that material was 300 psi unconfined compressive strength. That's almost a type 2 error. Type 1 error is you don't get any strength out of it at all. It doesn't do you any good. Type 2 error is that it's too strong to get through when you have to cut. You have to go back and drill your shaft through it. And we were right on the verge of being a type 2. During the excavation, we were able to go in a dry and look at the cobbles, and we found that they were actually distributed with thin layers of gravel and sandy material between layers of cobble. But we were able to get through it and get the shaft down. The geotechnical report also indicates that right here, the blue-green layer is repeated underneath the tunnel grade. When we looked at the bottom of the shaft, we found that there were cobbles. The material was somewhat different than shown in this, but the tunnel machine manufacturer concluded that they could push through this and just modified the cutters a little bit in order to get through it. This is the only exploration sample that I have that showed any of the cobbles at all, and these were very, very small compared to what the as-built condition was. In the as-built, we found cobbles up to 24 inches in diameter. Unfortunately, I don't have any photos that we took in the bottom of the shaft. Once we launched the machine, progress through the stabilized material and the breakout block was as expected. Cutting return was normal. Everyone uncrossed their fingers and went home, taking a nap. And as soon as the machine broke out of the breakout zone, it advanced about 10 feet and went offline, just way offline, jammed up and couldn't be pushed forward or pulled back. The answer was to go back in, open the airlock, hand mine out around the machine and jack it back into alignment. But as soon as you open the front of the machine, the water inflow is humongous. Even difficult to close the ports back up. So the next step was to inject bentonite slurry and fluid loss control agents ahead of the machine and try to create an impervious zone to reduce the water inflow. As soon as the ports were opened, though, after injecting the bentonite, the groundwater pressure pushed the bentonite right back into the machine. So the next level of intensity is using compressed air to balance the water pressure. And using compressed air also means that you have to use trained divers instead of laborers to go out in front of the machine. And the divers have to work with decompression, and it's a much more complicated and expensive process. And as soon as we tried that, we lost all the air. The material was so pervious that we couldn't contain an air bubble in front of the machine. So the alternatives for freeing up the machine were using a CSM system to construct another shaft, dig up the machine, or use grouting methods to form an impervious zone that would contain an air bubble right in front of the machine. And constructing a shaft was dismissed as way too expensive and a last resort because of the cobble layer that we'd had so much trouble getting through in the first place. Design of the tunnel intervention grouting is dependent on a thorough understanding of the ground condition and the properties of the grout. Permeation of the cobble material was successful in the shaft, but there were strings of gravel and sandy material that didn't get permeated with cement bentonite at all. And we didn't think that would hold air very well. So we set out looking for a different kind of grout material. And the criteria that we had to meet were low permeability and control of placement location, the strength of the grout, no type 1 or type 2 errors, and we had to be able to advance the machine after grouting. There were some other factors that we had to consider, but they aren't included in the criteria list. And these are availability of the necessary grout quantity, suitable mixing and pumping plant availability, drilling injection ports, and skilled labor. And finally, we need to get the owner and the project engineer of record on board with whatever material we selected. Every type of grout except sodium silicate is impermeable to air. Cement bentonite was ruled out because the permeation results in the shaft walls weren't favorable. Polyurethane grout was ruled out because it bonds to steel. Think of it like Gorilla Glue. But acrylamide and acrylate grouts met all the requirements, but acrylate grout begins to increase viscosity and is a little more difficult to place accurately than acrylamide. The set time and control for the acrylamide seemed the most favorable, and it was selected for this project. Oh, I've lost my mouse. Ah, here we are. Using what we learned with the grouting at the cobble zone and my own experience, I decided we had a good chance of getting permeation in the soils using small overlapping injections in the pattern that I've shown here, the tunnel machine and a series of overlapping zones that would form an arch above the tunnel. The pattern is based on 4-foot diameter columnar injection zones with 25% groutable pore volume. That's 2 gallons of grout per cubic foot of soil. The holes are laid out with 44% overlap between columns, and the injection points are 2 feet 9 inches center to center. In the 2 rows ahead of the machine, we skipped the bottom injections so that we wouldn't have to mine out grouted material in front of the machine. The outer rows were grouted first, and the inner rows were used to close up all of the gaps and form a lid above the tunnel. We only used 1 row right or left of the tunnel, but we used 3 rows of injections above the crown in order to make sure that we didn't have any vertical migration of the air bubble. The arrows show the potential short paths for the air to escape. But the one at the bottom here is interesting. We actually calculate the total waterhead at the invert of the tunnel. The air pressure is balanced just to push the air out to this elevation. At that point, there's 3 feet of pressure differential in groundwater between the bottom of the tunnel. So we're only looking at 3 psi air driving it out through any of these pathways. I'm going to switch gears a little bit. And this is a kind of a stylized view I stole off the internet of a soil deposit. In order to lay out a grouting pattern, you need to understand the mechanics of the grout flow in a granular soil. And this soil deposit consists of a wide range of distribution of particle sizes, from very small, microscopic, to very large, in this case, 24-inch cobbles. The key parameters for groutability of the material are the pore aperture and the total pore volume. And the pore aperture is actually equivalent to or approximated by the D15 of the soil. D15, it means that 15% of the particles are smaller than this number, 85% are larger. The groutable pore volume of the soil is always less than the actual pore volume. The reason is that some pores are too small for a grout to get into. Some groundwater remains trapped in the pores, and there's some dilution of grout by the groundwater as the injection is going on. But for most cases, 15 or 25% of the total volume is a good estimating number for the total pore volume that you're going to grout. 15% is equivalent to 2 gallons per cubic foot. The pore volume is almost constant in granular soils. If you look at this illustration, if I expand each of these pores or each of these particles by the same amount, the pore space in between has to expand by the same amount. So it's always, once you determine the pore volume, it's a constant whether you go from the finer grain to the coarser grain portions of the project. The pore aperture, however, is completely dependent on the grain size, and it's equal to the D15 of the grain. So if we go from sand, which has a D15 of about 3/1000ths of an inch, to the cobble zone where it's 3/100ths of an inch or more, the permeability increases with the cube of the pore aperture. So in this case, going from sand up into the cobble zone, we get a permeability increase of over 1,000. In preparation for grouting, you need to drill a hole into the soil deposit, insert a porous port of some sort, and there are many different styles of ports, and then the grout is injected out through the walls of the port. This illustration shows grout in the injection port. There's some dilution of grout as it spreads, and the distance that it travels is related to the volume of grout that you've pumped in by this equation. D equals the cube root of the volume divided by 0.524. This is true for isotrope or uniform deposits of material where the soil permeability is approximately equal in all directions. If we're in stratified deposits, the permeability can be up to 10 times in horizontal what it is in the vertical direction, and you would actually have a square root term in this equation instead of D. But for this project, the deposits are very uniform permeability, and I used the cube root equation. Going back to this slide, I added a model of single point grout injections. And keep in mind that the actual injections are a lot more irregular than this. And but they follow basically this pattern. The first step in the layout is drawing the shape of the grouted material zone. Then you lay out a group of small diameter injections throughout the zone. And it's a matter of experience about how much size or what diameter you want to use. But as a general rule, it runs between 3 and 6 feet in diameter. The spacing between shots should be arranged so that primary and secondary pattern like this is used. You inject the primary points, they more or less confine the secondary points. And when you go back to inject between them, then the grout is forced to seek out pathways around the primary shots and complete filling up the zone it, much more thoroughly than you would if you're just putting out an isolated single point shot in an undisturbed area. In this case, I calculated the primary shots to fill roughly spherical volumes with a 2-foot radius of travel. And the primary shots are spaced 5.5 feet apart. And that means that the secondary shots are only 9 inches away from the edge of any primary grout injection. The grouting turned out to be 100% success on this project. We completed the work about 6 hours ahead of schedule, and we were under budget. That's always good to be under budget. This photo is the grouting pattern layout from the ground surface. There are rows of points, and there's not very much to see from the surface. The work started during very cold weather. One of the chemicals was exposed to cold on the way to the job, and it froze up, had to be melted. And we had to track the injections where the material froze in order to be confident that we didn't have any problems. It turned out that was a non-issue, by the way. The injection ports were drilled using a typical rotary percussion drill rigs and 101 millimeter tooling. And the injection pipes were lowered in the hole by a crane after the drill steel was extracted from the hole. Then the annulus between the pipe and the ground was filled by washing a fixed quantity of sand down the hole. Sand is pervious to the grout and helps to control it entering the ground at the right place. The injection pipes were black steel, Schedule 40, merchant couplings. They're 21-foot sections, and they were coupled together. Then a pulling head and hose connection was hung from the crane and connected to the end of the pipe for each injection. As soon as a fixed quantity of grout was pumped down the hole, the crane would lift the pipe to the next stage, and we'd make another injection. Later on during the project, when we were doing the secondary holes, we had to change the gel time of the grout a little bit because the grout was going in slower. Also, many of these pipes went down in front of the tunnel machine, and even though we hadn't lost any pipes when we were grouting in the area before the shaft was constructed, we decided that the risk of losing a pipe in front of the machine was too great. So we replaced the bottom end of all of the pipes with PVC Schedule 40 pipe that could be ground up by the machine. It was a very simple seal at the bottom of the pipe. We drove a machine bolt in there, taped it in place with duct tape. When we're ready to start pumping, we just put about 100 PSI pressure in the hole and blew the bolt right out of the end. For simplicity on this job, we hot batched the acrylamide grout. Hot batching means that you mix it all in one tank and you add the catalyst to the tank instead of pumping it together at a Y. We set the gel time to give us about 10 minutes cushion to get all the grout into the ground after we catalyzed the batch. Things went along pretty smoothly. We only lost one batch that went off too fast. Anyway, that's my recollection of how much we lost. The injection work was completed on a Saturday night shift, and 4 hours later, the tunnel machine operator started pumping air. And after a couple of hours, pressure built up, the rate of air loss stabilized, and the divers arrived on site Monday morning. The first entry was completed by noon, and the bubble in front of the machine was maintained through the entire work period of 5 days after that, with no significant change in the rate of air loss. When the divers succeeded in loosening the machine, it restarted, and after about 30 feet, we broke out of the cobbles and went into a new surprise, which was Mount St. Helens ash, which never showed up at all on the exploration logs. I have to go back. Is there some way? There we are. We go back to this map. I want to show this slide for a moment because we did hit this Mount St. Helens ash, and it continued this way, and it's very abrasive, and it began to wear out the cutter teeth on the machine. We got down about this far, and this area was held up by eminent domain. When they got the lawsuit settled, they had just a very narrow easement from about this location over to the shaft, and that was only for the tunnel machine. There was no room at all to go in and do an intervention. The owner decided at that time that rather than take a chance on getting stuck before he got to shaft D, he shut everything down, and we did another intervention similar to the first one, and went back in and changed the cutter teeth before they pushed through to this D. But that's another story for another day when we're talking about acrylate grout. So with that said, the end. So I can turn this back
Great
to
job, Ken.
And
that was a fantastic presentation.
Yeah, it was great. I appreciate that. So I do want to hop in real quick because we are running a little bit low on time. We've only got 3 minutes until 12:15, which we need to try and stay privy to our registrant's time frame. So we're going to skip Q&A for this portion. What we'll do is we'll take all the questions that have been submitted and answer them, and we will next week send an email with some follow-up, including a recording of this webinar, some other information. But just before we head out of here, we wanted to give Ken just another minute. You heard at the beginning that he started grouting in 1966 and has over 800 different projects, but he has one in particular that's his favorite. So we wanted to give him a moment to explain it, and then have Ken, Jake, Britt give a final, goodbye, thank you, and we'll jump off here. So Ken, you're on again.
Okay. Well, when I was asked to single out my favorite project, it was a no-brainer. It was the Palace of the Legion of Honor in San Francisco. The Palace of the Legion of Honor is a fine arts museum. It was up for seismic retrofit in about 1990. It was built by Alma de Bretteville Spreckels and dedicated as a war memorial to San Francisco soldiers killed in World War I. It was built in Lincoln Park, and Lincoln Park is the terminus, the western terminus of the Lincoln Highway, which was the first paved highway that went clear across the United States. It starts in Times Square in New York City and is now known as US Route 30 all the way across the US. The Palace of Legion of Honor is the home to one of the original castings of Rodin's The Thinker, and it was a massive project. I was selected as the underpinning contractor, and we pumped about 100,000 gallons of chemical grout, sodium silicate based grout, underneath the front facade of the palace. And under the north wall, we pumped about 40,000 gallons to stabilize the ground before they drove a new utility tunnel under the basement of the museum. And part of the reason it's my favorite is that the reopening of this was a gala affair that people, politicians, literary people, all of the glittering officials of the San Francisco area attended. I rented a tuxedo for it. We drank champagne and danced away the night. It was really a memorable project. And with that, I'll turn it back to Britt, Jacob.
Yeah, thank y'all. Go ahead, Britt.
Thank you, everyone. What a great presentation, Ken. I really enjoyed getting to see that. I think you were just wrapping that project up when I first stepped into injection grouting 13, 14 years ago, if I remember right. And I've had the privilege and the honor to get to be your friend, call you friend since then, and I've been grateful for that. Wanted to share with everybody, we do have an industrial and geotechnical injection grout school coming up, April 24th, 25th. Ken is going to be, you want to see him live and in person. Ken's graciously going to come be a part of the school and help share his knowledge on a face-to-face basis. There's nothing better than being belly to belly or toe to toe and getting to learn from each other. 2 days of great knowledge share. We share what we know. We love to have you share what you know in attendance. So we invite anybody and everybody that would love to come to that. It's here at Avanti HQ. So if you're in the northern hemisphere or the northern part of the upper latitudes and you're looking for a little warmer weather, it's down here in Webster, Texas, just a burb of Houston, and definitely promise you it'll be a little bit warmer. It won't be too hot, but be perfect, good weather. So Ken, I'll hand it over to you. Just some closing thoughts.
Yeah, if you have any 10, 15 seconds closing thoughts, and we can end this. We're about a minute over, and we'll end this thing for everybody.
Well, I hope that everybody can attend to the grout school. It'll be really fun to meet everybody face to face instead of in this kind of sterile environment here.
Yeah. Thank you, Ken, again. And Jake, any last closing comments from you?
I just want to thank everyone for attending and thank Ken for the presentation. This is a project that I've always been very interested in since hearing about it first, and it's great to get the details. Hopefully it drives home some of the unique applications and what can be done with a grout and kind of sparks everyone's curiosity on where these products can be utilized to benefit you. With that, wrap things up.
Great. Thanks, Jake.
Yeah, and I'll round it out, and I'll mirror what Jake said. Ken, it was great to see how you guys used such a myriad of different product or grout injection types to accomplish that project, and love the presentation. Thank you everyone for attending. Our contact information is here on the slide. If you need to get in contact with us, have questions, we're happy to help. We've got a great amount of technical resources available. Ken's available as well. And thank you, everybody. Jessica, I'll hand it back.
Sounds great. Thank you all. And one last closing comment from me is that be expecting a follow-up email. We'll have the questions answered that were submitted. We'll have this contact information from the presenters as well as some other information. It'll probably be mid next week. So keep an eye out for that. But if you have questions in the interim, you know how to reach us. And with that, we'll end this webinar and send you on to have a great rest of the day. Thank you, everybody.
Take care.